Hi. Dear fellow FX artists and TDs. In computer graphics, Hooke's law is an essential concept used in simulations of deformable objects, such as cloth, and other soft bodies. This principle can also help us understand the inner working of solvers such as Vellum and Houdini, but more on that later. To simulate cloth, computer graphics artists and engineers use a model called the mass spring system. The mass spring system models the cloth as a collection of particles connected by springs. When a force is applied to the cloth, such as the gravity pulling, these string deforms, and the particles move accordingly. Hooke's law is used to determine the amount of deformation produced in the cloth when a force is applied. The stiffness of the springs connecting the particles is determined by the material's physical properties, such as its elasticity and Young's modulus. Let's take a look into how this can be done in Houdini. The standard method is to use Vellum solver. And to be very honest, it's the only recommended and the best way to make these kind of effects. And of course something very complex can also be done using Vellum solver as well. But my purpose for this video is to help you all explain how these solvers work under the hood. How does a point just magically starts to fall under gravity? What's the math and physics behind it? So for this demonstration, we're going to make a simple version of Vellum solver that simulates a particle behavior under the influence of gravity and spring force, and let's call it Hooke's solver. Let's jump into Houdini, and for starters, let's make a simple particles that falls under gravity. Now, before I make anything, let me explain the science behind a free-falling object. Now in real life, if we have any object or even a single particle on a given coordinate, it should be completely static, as long as no force is applied on the particle, and it has no mass. So as soon as a particle having any amount of mass except 0, and it's under influence of any force, it should be moving in the direction of applied force with a certain speed. Nothing too complicated, it's just some basic physics. But now let's discuss a bit more advanced, but simple, equations, which we're going to utilize in the setup. Let's start with force itself. I know many of you may be familiar with the formula, which is force being equal to mass multiplied by its acceleration. But, hear me out, while this formula is correct, many of us may start to quickly rearrange the variables and calculate the acceleration, and, hence, the velocity using the equation of motion. But chill. Take a breathe, let's actually think about it for a moment. When I say force, what I actually mean is a net force. Meaning not only gravity, but any other force, which may be there acting on the particle, for example, a wind force, or a spring force, which we're going to implement in the next step after this, is determining the acceleration of the particle. So in this case we're going to use this formula to derive the acceleration, and then, using the equation of motion, we can calculate the velocity. Let's actually jump into Houdini and start doing this. Let's start with making a single particle, or point using an add node. Once we've done that, let's add an initial velocity to this particle. Now, we can make a solver node, and call this Hooke's solver. Let's jump inside the solver, and add a wrangler node. Let's lay some variables out, starting with a time step and set this equal to 1 divided by a channel. Let's add a mass variable to give our particle some mass. Now, let's make a gravity force vector. For this example, let's actually also add another force, acting due to the wind's acceleration. For now, as we're only making a free-falling object, let's skip the addition of spring force, and just set the total net force as force_gravity plus force_wind. Now, we can calculate the acceleration of the particle due to this net force. Now, let's use the equation of motion to update the velocity vector. Notice that I am using the v itself as initial velocity, as we're in a solver node which gets executed every frame. Now, we can update the position as well by just adding the position to the velocity vector. Notice that we're multiplying the time step value to the velocity here, as we need to update the position every time step rather than every frame. Let's set some values in the channels, and link this value to the solver's substep, and move out of the solver and play the animation. Awesome. We've done it. The particle is now falling due to gravity, and also accelerating. Notice that the particle even jumps up for a few frames due to its initial velocity. Also, the wind force here is working as expected. All that's left is to implement the spring force into this solver, so let's do that. But first, let me explain what we're going to do. Now, let's imagine what will happen when the particle which is falling has a spring attached to it, and the other end of the spring is attached to a wall. We can use the Hooke's law to determine another force which is acting on the particle due to the spring stiffness. Let's see the formula for the spring force. So from Hooke's law, we have this formula, which states, force acting on a particle under the influence of a spring would be equal to negative of the displacement multiplied by its stiffness value. So it's clear that this force will make our particle dangle at a distance that will be inversely proportional to its stiffness value. Let's jump back into Houdini and implement this formula in the solver. Let's add a new variable for the stiffness. Now, let's add a hypothetical pivot position vector which will act like a pinned end of the spring. I'll drive this vector with a reference to a position through an add node. It'll be simpler that way. Let's now set a displacement vector, which will be the difference between the current position and the defined anchor position. Now, we can define the spring force using the formula we just saw. Amazing! Let's just add this force to the total net force. This should do the trick. Let's jump out of the solver and run the animation. Oh. Something's wrong, we're not in trouble though. Actually, the force is working exactly as it should, but its energy is not depleting as it should in real life. That's why, in computer graphics, we have this thing called damping. So what is damping? Well, it's just an amount, at the rate of which a certain oscillation loses its energy, hence, coming to a halt. We can very simply just update the velocity multiplier at each step, right before we're calculating the spring force, and we can damp the incoming velocity. Let's make a channel reference for that and just use a small value like 0.8 on each frame to deplete. If it's not already clear from the formula, just know that the lesser this value, the more the damping. Let's jump out of the solver and run the animation once more. Hooray! We've done it! The particle is now behaving as if it's attached to a string. We can also add a line between the 2 points for better visualization. Notice how the string is also taking the initial velocity into the account while constraining the particle. And that's it. We've made what we wanted. Now if you think about it for a moment, you can understand how most of the soft body solver works in Houdini. You may now have more understanding of why in most of the solvers, damping plays an important role. Now I'll quickly walk through another example I have prepared for this as an application of what we've learned. In this example, I created a line. Then, I will convert the line, so that I have primitives for individual segments. Now see how I am storing the pt_num value for each primitive's adjacent points to store the point for its pivot's position. Here, I am also setting a condition for the very last point, to store the previous adjacent value as the pivot point number. Then, I have created a point group, to pin the point, and animate it. Now I can use the Hooke's solver that we just created. But I changed a few things first. In the solver's code, now, instead of using a custom pivot position, I am just using the position of incoming pivot points we stored earlier as a pivot. Also notice, I have a second input here as well. This input is just for the animated data which we're storing as a pos vector variable, which I am just using in the very end, to update the position of the pin points. Let's see what we get. Amazing! You can see the possibilities are endless. Now you can even have multiple lines here. Let's also introduce some variation in mass for each points. See the effects of different forces. Okay. I hope I was able to demonstrate something useful here. You can further read about effects of different forces and their formula, and also try to explore further. Just remember that the acceleration is being driven here by the collective net force of any number of forces. Also, this method doesn't take collision into account yet. But do let me know, in the comments, if that's something you'd like me to explore as well. Till then, I am out. Thanks for watching.